So 13.3 is about a thing called geometric sequences. So the first thing we had to be kind of creative. Yesterday it was all arithmetic, meaning add a lot of stuff. Today's geometric. Geometric means you have a common ratio, which just simply means you're going to multiply the same number repeatedly. So like for this problem, what's the common ratio in this? 2. We're multiplying by 2 every time. Times 2, times 2, times 2, times 2. That makes it geometric. Ratio is 2. Ratio on this one is 3. It's geometric. Ratio is 3. Question about the concept of what puts this into today's world. So here's a formula that by the time the test comes you want to know. Or you could be super skilled at the creative way we did 13.1. If you were super awesome at 13.1, you don't need any of the formulas except the sum formulas. But this is the general term formula for geometric. You want to take the first term times the ratio. The ratio gets a power, which is always just n minus 1. This is easier than arithmetic. So the general term for this one, you just grab the first one, 3, times 2, we decided was the ratio, and just put on there the power of n minus 1 and stop. Quit while you're ahead. It might be tempting to take 3 times 2. You can't do that. If this is to a power, order of operations from your younger days, parentheses were 1, exponents are 2, multiply has to wait for a while. If you can't do this power, you can't multiply yet. You just sit and wait. Question about general term there? So what would be the general term for this one? 9 times 3. Power is n minus 1. Question about that? The only way you can put these together at this point is if you luck your way into a situation like we're in right now, if I can get a little creative for a second. 9 is a power of 3. What is 9? 3 squared. When you have the same base and it's multiplying, back in our Algebra 1, Algebra 2 days, what could you do to the powers when you were multiplying and the base was the same? Added them. So if we add 2 to this, combining as best we can, that would be n plus 1. I don't care which answer you have, but if you have something like this and you look in the back of the book and they have that, maybe they did that. If you were doing this lesson the creative 13.1 way, maybe you'd have gotten there to begin with instead of here. I don't know what you would have created. But the only way those can go together is if somehow they have or can be forced to have the same base. Question about that starter? This is a strange chapter because I think every day gets easier. I think 13.1 was the harder day. 13.2 I think was easier. I think this is easier to navigate than 13.2. Tomorrow will be easier than this. So here's another sequence. I'm asking you to find the 6th term, which isn't that far, so maybe you'd be tempted to just take 3 more hops. I don't know. But I'm going to work through the general term. So if I take that sequence and I work through the general term, what would the general term be? 3 times negative 5 to the n minus 1. Which could lead us to the 6th term if we just plug in 6. So we could go 3 times negative 5 to the 5th. I'm throwing that in parentheses because you have to for calculator purposes. If you punch into your calculator negative 5 to the 5th, again the order of operations would jump in. It would do 5 to the 5th, and then just throw a negative on it later, which might or might not be what you want to do. In this case, it works out the same, because if we do this, the negative counts singly. If I do that, now I've got 5 of that negative. Negative 5, negative 5, negative 5. There's 5 negatives involved. But whether there's 5 negatives or 1 negative, I guess you'd skate on that one and it would work either way. It's the same. Calculator, little punch, punch, punch. I think it's 9175 negative. My paper will know. 9375. My paper was better than I was. Something about that? Yeah.
What is the negative 5?
The ratio. So from here to here, multiply -5. From here to here, multiply -5. Yeah, if you're not sure how we're finding the ratio, anybody that's too shy to ask, divide any term by the one before it. It doesn't matter where you pick. You could divide the third divided by the second divided by the first. Take any term in the list and divide by the term that came before it, and that would tell you the ratio in any circumstance. Question about that? The yesterday video had arithmetic means, where what was happening was add, and you had to figure out how to add the same number a bunch of times to connect the dots. Today they're going to do a thing called geometric means. So if you're told to insert 2 geometric means between 10 and 80, it means there's 10, there's a mystery number, there's another mystery number, and then there's an 80. And we're trying to figure out what those mystery numbers are. If the book gives you an artificially easy question, you can just try to trial and error it. Sometimes that works. Okay, this is an artificially easy question. You could just try to multiply by a number and see what happens. Pick a number that we might be multiplying by. 2. So 10 times 2 is 20. 20 times 2 is 40. 40 times 2 is 80. That is our number. Boom. If they go easy question, you can just jump on that. That's not a real effective trick to rely on that. So if they're multiplying by 1.72, I don't think you're going to luck your way into that. That seems unlikely. So here's the scheme to do this. If they're going to multiply, what math thing got invented for multiplication, repeated multiplication by the same thing? Some sort of power. Okay. So what's going on here is we have a power of 3. What total multiplication has occurred from beginning to end? The multiplication totally multiplied by 8. We're trying to undo this. So the question on hand now is, what undoes a third power? Cube root. If you do the cube root of 8, that's going to tell you what we're multiplying by. The cube root of 8 is 2, so we are indeed going to hop to 20, to 40, to 80, and then we're good. Question about that? I'll just talk while I move the camera to get it over here. And the last thing of the day is finding the sum of a sequence like this. So if we're going to find the sum, we've got some new and improved formulas compared to the add formulas. So there we go. The sum formula is going to be, when you punch this in on the calculator, you're going to need parentheses around whole top and whole bottom. When formulas are written, they're there, they're visible. On the calculator, you have to make them visible. But for the top of this, we want to take the first term minus the first term again, but this time it's multiplying the ratio. The ratio has to go to a power. The power there is going to be how many numbers you have. On the bottom, we're going to go 1 minus the ratio. That's a formula you're going to need for the test to get in your brain somewhere. If you do the parentheses around the top, do the parentheses around the bottom, the calculator handles the rest of the lifting. The calculator knows the order of operations. It'll do the power first, it'll do the multiply second, saves and subtract the third. You don't have to worry about that. But if I want the sum of the first 13 of this thing, what would you start with? 3 minus 3 again times, ratio is 5 because every time I'm multiplying 5, power is 13, bottom is 1 minus the 5. Parentheses here, push a lot of buttons. I'm not even going to try to do that in my head. 5 to the 13th would be ridiculous. This should kick you out 915,527,343. Something there. Same formula applies. This is just being presented to you in a different way. The sigma symbol means we're adding it up, but we're going to have to figure out what is the first term. So how can you figure out what is the first term? Yeah, take the 1 from the bottom and not necessarily. How can we figure out the first term of this thing? Plug it in. Take the bottom number, plug it in. So what this is designed to do, if you want to know the first term, you plug in 1. If you want to know the second term, you plug in 2. If you want to know the last term, you're going to have to plug in 15. That's what this can give us, any term. So to figure out the first term, plug in 1. 1 minus 1 makes 0. What's anything to a 0 power? 1 times 6? 6. So the first term is 6. So 6 minus 6 times, we don't know the ratio yet. What's the power going to be? 15. And then we need 1 minus the ratio. Well, the first term was 6. How can we figure out the ratio? Get the second term and divide it would be one way to do that. Second term, plug in 2. 2 minus 1 is 1. 2 to the 1 power is 2 times 6, 12. The second term would be 12. So if the second term is 12, the first term was 6. What's the ratio? 2. Stick in a 2. Stick in some parentheses. Press a lot of buttons. This isn't going to be as big, even though the power is higher. 5 to a power adds up a lot faster than 2 to a power is going to. It's still pretty big. It's 196,602. Alternative plan to figuring out the first and the ratio. The camera won't be able to follow along, but if we look at the general term equation, if you see an n minus 1 power, which we had a k minus 1 power, same thing. The general term formula is designed to reveal for you the first and the ratio. The first is the only number by itself. The ratio is the number that goes to the power, but you can only use that little sneaky trick if the power is variable minus 1. If the power is variable minus 1, in a way they gave you the first and the ratio already right out of the gate. That's all today is. Those couple of sort of schemes. The homework that builds off of this is on a 571. 571's going 1 to 24. In this section, we're just doing everything. I think some of the other ones we had like an even odd threes or something, kind of a thing going. But 571, we'll just head it up to 24. Tomorrow, 13.4 is infinite geometric series and adding them up, and it feels like that should be a lot harder and it's a lot easier. So infinite geometric sequences tomorrow is that. Give you a review sheet. There's a test coming soon. This chapter's over after 13.4.